Tonight, we're going to follow a single invisible impact that almost no one on Earth noticed. No buildings shook, no alarms went off, the sky did not glow. Yet, in that moment, a ghost particle slammed into our planet with around 30,000 times the energy of the most powerful collisions at CERN's Large Hadron Collider. A force that outclasses the greatest machine in human history and passes straight through you without a whisper. On the frozen plateau of Antarctica, the night was calm. Above the South Pole, space looked empty, a quiet corner of the solar system, but buried a kilometre beneath the ice, more than 5,000 glass spheres watched in perfect darkness. They formed the IceCube Neutrino Observatory, a silent cubic kilometre of crystal-clear ice, waiting for something that almost never happens, waiting for a neutrino with absurd energy to finally fail at being a ghost. Trillions of low-energy neutrinos are streaming through your body every second, born in the nuclear furnace of the sun, and in distant, exploding stars. They pass through planets, spacecraft, and entire worlds as if matter were an illusion. Almost none of them interact. Almost none leave a trace. But this one was different. This one had crossed billions of light years, maybe since before our solar system finished forming, and when it reached Earth, it left a detectable scar in that Antarctic ice. In a fraction of a second, it struck an atom hidden deep below the surface. The impact launched a charged particle faster than light can travel through ice, creating a cone of eerie blue Cherenkov light. Sensors recorded a sudden flash, then another, then a cascade, like a ghost, drawing a line through the darkness and vanishing. From that pattern, scientists could reconstruct its path. This neutrino had been aimed almost like a bullet, straight at Earth from far beyond our local neighbourhood of planets. For over a century, the mission of high-energy physics has been to build ever larger machines to smash particles together. Gigantic rings, superconducting magnets, billion-dollar colliders pushing closer to the limits of technology. Yet on this night, the universe casually outperformed all of them. No one predicts a single natural particle carrying tens of millions of times more energy than anything the first accelerators could reach. Absolutely no one anticipates that deep ice would become the stage for one of the most remarkable scientific detections in human history. By the end of tonight, you're going to understand how a ghost from the edge of the universe can outshine CERN, or what kind of cosmic engine can hurl a single neutrino to such extremes, and why catching it forces us to rethink our place in a violent, high-energy cosmos. What hurled this particle across intergalactic space? Why did its path intersect this tiny blue world? Now, let's begin. To understand why this one ghost particle is so unsettling, you have to start with what was supposed to be the pinnacle of human control over high energy. For decades, the crown jewel of particle physics has been a ring buried under the French-Swiss border, the Large Hadron Collider at CERN. It hurls protons around a 27-kilometre tunnel and smashes them together at energies of about 1 trillion electron volts, 10 to the 12th. For a human-built machine, that is extreme. Engineers chill superconducting magnets to near absolute zero. Scientists choreograph beams of charged particles with exquisite precision. The whole mission is to recreate, for a tiny moment, the conditions of the early universe inside our own solar system. Before we get started on the ghost, remember this. The LHC is often described as the most complex machine ever built. It has been the pride of modern engineering and the symbol of how far our species can push matter and energy. Now, place that pride next to what arrived from deep space. In 2022, buried instruments in Antarctic ice recorded a single neutrino carrying tens of thousands of times more energy than those LHC collisions. One particle, not a beam, not a ring of magnets, a lone ghost that had been travelling across the cosmos with roughly 10 to the 16th electron volts locked inside it. The boundary between human achievement and cosmic reality suddenly looked very small. This is the contradiction, designed for a trillion, hit by something 30,000 times higher. The universe, without funding proposals or superconducting coils, had taken a single elementary particle and accelerated it far beyond the reach of our largest collider. No one expects a natural accelerator to outperform CERN by that margin. No one predicts that a neutrino, famous for barely interacting with the matter at all, would be the messenger that reveals it. The questions cascade. Where did it come from? What kind of engine out there among the galaxies and planets can grab a particle and fling it to such absurd energies? Why did it arrive from that particular direction in the sky, threading its way through the solar wind, through the magnetic fields of the Milky Way, and straight into a cubic kilometre of ice at the South Pole? And if one such particle has been caught, how many more pass through Earth every year, every day, without leaving a trace? Tonight, we're going to turn that unease into a roadmap. First, what neutrinos actually are and why scientists call them ghost particles. Then, how the IceCube Neutrino Observatory turns Antarctic ice into a giant telescope for invisible messengers from beyond the solar system. After that, the story of this specific 2022 event. How the signal was recognized, how its direction was reconstructed, and how its energy was calculated. Finally, the leading ideas about its origin, blazars, active galactic nuclei, titanic jets powered by black holes at the hearts of distant galaxies. By the end of tonight, you're going to understand how this single neutrino forces a rewrite of our models of extreme energy. You'll be able to picture an invisible high-energy universe all around us, a universe where space is filled with particles far more intense than anything we can make on Earth. And just when that picture starts to feel stable, the data from IceCube will push it right to the breaking point. So if you're still here, listening to scientists argue with the universe about a single ghost particle, that already says something about you. You're not just skimming headlines about space. You're the kind of person who wants to understand what's really happening in the dark, violent corners of the cosmos, where the rules of the solar system get pushed to the breaking point. Most people stop at, IceCube saw a crazy neutrino, cool. You want to know how a particle 30,000 times more energetic than CERN's collisions can cross unimaginable distances, thread through planets, and then, by pure chance, light up 1 cubic kilometre of Antarctic ice. That curiosity is rare, and it's exactly who this channel is for, because topics like this are not easy. Ultra-high-energy neutrinos, Cherenkov light cones, cosmic accelerators far beyond our planets and beyond the boundary of the solar wind. None of that drops out of a textbook ready for animation. To turn a blizzard of research papers into a clear picture that you can hold in your head, scientists' raw data has to be unpacked, cross-checked, and then rebuilt as a story that still respects the physics. That means time. Time to read what mission teams from IceCube publish, time to compare energies from the large Hadron collider's 10^12 electron volts up to the 10^15 and 10^6 electron volt monsters the cosmos fires at us. Time to design visuals so when a neutrino carves a blue streak through Antarctic ice in the video, you actually understand what that light means, and how a detector buried under the polar wind can reconstruct the particle's path back across intergalactic space. Before we get started on the deeper history of these ghost particles, there's one quick thing that makes a huge difference. If you love diving into deep space mysteries and frontier physics like this, a like on the video or a fast tap on subscribe helps more than it seems. It's low friction for you, but it tells the algorithm that long-form, nuanced stories about weird particles and extreme missions are worth showing to more people. No one expects a neutrino video to compete with viral clips. No one predicts that a careful breakdown of IceCube's data will get recommended to someone who has never even heard the phrase cosmic ray. But engagement is how that happens. Every comment, every watch through, every share pushes these quiet, difficult topics a little higher until absolutely no one anticipates how many new curious minds they reach. So, now that we're on the same team of cosmic detectives, let's pull the camera back. Tonight, we're going to step away from the South Pole for a moment and rewind history to a time when neutrinos were just a desperate theoretical fix. To understand why this one particle is so shocking, we have to see how ghost particles were discovered in the first place and why, for decades, they barely left a trace at all. Now, let's begin. The story of ghost particles starts with a crisis. In the early 20th century, scientists were watching certain atomic nuclei spit out electrons in a process called beta decay, and the numbers refused to add up. Energy seemed to vanish. Momentum went missing. If that was true, one of the deepest rules in physics, the conservation of energy, would be broken right inside the atom. This is not a small bookkeeping error. Conservation laws are the bedrock of the entire solar system, of every mission, every spacecraft, every orbit of the planets. If energy can just disappear in radioactive decay, then nothing in space or on Earth is truly predictable. Some researchers even wondered if these laws might only be usually true, cracking open at the quantum level when no one was looking. Then, in 1930, Wolfgang Pauli did something bold. Before we get started with cosmic neutrinos and Antarctic ice, the story has to pass through a single, desperate letter. Pauli proposed an invisible particle hiding inside beta decay, stealing the missing energy and slipping away undetected. It would be electrically neutral, nearly massless, and interact so weakly with matter that no detector on Earth could catch it. He half joked that he had done a terrible thing, a particle that could never be observed. A few years later, Enrico Fermi took Pauli's ghost and built a full theory around it, giving the new particle a name. The neutrino, the little neutral one. On paper, it solved everything. The energy came back, momentum was saved, the accounting balanced again. But there was a catch. For decades, neutrinos existed only as equations and diagrams. No one expects a particle that barely touches matter to be easy to find. To understand how elusive they are, imagine a wall of solid lead stretching for light years through space. A neutrino could fly into that wall and, in many cases, come out the other side, as if the entire system weren't there at all. Trillions of solar neutrinos from the sun are streaming through your body every second, through the planet beneath you and out the other side, leaving almost no trace. In the 1950s, that changed. Experiments near nuclear reactors finally caught neutrinos in the act, seeing rare flashes from their interactions with matter. A little later, detectors buried deep underground began to register neutrinos arriving from the sun, confirming that nuclear reactions at its core were real and that neutrinos were a fundamental product of those reactions. The ghost had stepped out of theory and into the data. The boundary had shifted. What began as a fix for missing energy in tiny radioactive decays became a new way to probe the solar interior, the Milky Way, and beyond. By the end of tonight, you're going to understand how those same ghost particles, once feared to be undetectable, are now used as messengers from the most extreme engines in the universe, and how one of them arrived with an energy that absolutely no one anticipates. So, what kind of particle can vanish through planets, sail past stars, and still arrive at a detector on Earth with the punch of a fastball? To answer that, the mission has to zoom in on the ghost itself. Before we get started, forget glowing beams and crackling lightning. A neutrino is the opposite of cinematic. It is almost nothing. In simple terms, a neutrino is a nearly massless, electrically neutral particle. It doesn't feel the electromagnetic force that locks electrons to atoms. It doesn't feel the strong nuclear force that glues protons and neutrons together. It only talks to the universe through the weak nuclear force and gravity. That combination makes it the ultimate introvert of the particle world, sliding through matter as if it were mostly empty space. And for neutrinos, it is. Right now, every second, trillions of solar neutrinos from the nuclear reactions in the sun are streaming through your body, through the walls, through the entire planet. Almost none of them will ever hit a single atom inside you over your entire lifetime. The boundary between you and space means almost nothing to them. From their perspective, the solar system is transparent. Now, let's begin to classify these ghosts. Neutrinos come in 3 known flavors: electron, muon, and tau. Early on, scientists assumed each flavor was fixed, tied to its partner particle forever. But as detectors improved, something strange appeared. Neutrinos created as one flavor were being detected as another. They were oscillating, changing identity in flight. That shape-shifting behavior is only possible if neutrinos have tiny, non-zero mass, a discovery that forced a rewrite of the standard model of particle physics. To understand why that matters for this ultra-high energy visitor, compare a neutrino to 2 more familiar particles, a photon and a proton. Photons, the particles of light, are massless and electrically neutral, but they interact readily with charged particles and atoms. A thick slab of metal will stop most of them. Protons, on the other hand, are heavy, positively charged, and feel both the strong and electromagnetic forces. A single sheet of paper can block low-energy protons. Even the highest energy cosmic protons are bent and scattered by magnetic fields and gas as they cross interstellar space. Neutrinos are different. No electric charge, no strong force, no coupling to magnetic fields. A light year of lead would barely slow them down. That's why they can escape the densest cosmic engines, the cores of exploding stars, the maelstrom around supermassive black holes, the shock fronts, where the solar wind collides with interstellar gas. They are perfect messengers from regions every other signal struggles to leave. Tonight, we're going to focus on a single messenger that broke all expectations. If most neutrinos drift through the universe with modest energies, what does it mean when one arrives carrying the kinetic energy of a 90-mile-per-hour baseball compressed into a single subatomic particle? No one expects that. No one predicts a ghost particle outmuscling the world's largest collider. And absolutely no one anticipates that a cubic kilometre of Antarctic ice will be the place that finally catches it. Those numbers sound ridiculous. A 90-mile-per-hour baseball's kinetic energy squeezed into a single ghost particle, aimed straight, at the solar system. To understand how outrageous that is, you need to see where neutrino astronomy began. Now, let's begin with the quiet end of the spectrum. For most of the 20th century, neutrinos were gentle whispers, not cosmic sledgehammers. Early missions in this field did not chase monsters. They chased the faint, low-energy neutrinos streaming from the Sun and from nuclear reactors on Earth, the kinds of particles that barely nudge a detector, even when trillions pass through every second. Scientists built enormous underground tanks just to see a handful. A classic example, a vat holding tens of thousands of gallons of cleaning fluid buried deep in a mine, waiting years to register a few solar neutrino events. Designed for a 5-year mission to test solar fusion models, these experiments often ran for decades. The expectation was simple. The Sun's nuclear reactions should produce a certain flux of neutrinos. The reality was far stranger. They saw only about 1/3 to 1/2 of the predicted number. This became the famous solar neutrino problem. Prediction versus observation did not line up. Either the solar model was wrong or something was happening to neutrinos as they traveled through space. No one expects the most elusive particle in the standard model to rewrite the rules of particle physics. But that is exactly what happened. Over years of measurements from solar detectors, from reactor experiments, from neutrinos born in Earth's atmosphere, a pattern emerged. Neutrinos were not fixed identities, they oscillated. Electron neutrinos could transform into muon or tau neutrinos as they flew, changing flavor and evading detectors tuned to only one type. By the end of tonight, you're going to understand that this one discovery, squeezed out of a few low-energy events, forced scientists to accept that neutrinos have mass and that the standard model was incomplete. Crucially, the energies involved were modest. Solar neutrinos arrive with energies of about 1 million to 10 million electron volts. Reactor neutrinos are in the same ballpark. Even core collapse supernovae, among the most violent explosions in the cosmos, typically spray neutrinos with energies around 10 billion electron volts. Powerful, yes, but still toys compared to what the upper end of the spectrum can do. Think of the neutrino energy spectrum as a map. At the bottom lie relic neutrinos from the Big Bang, so low in energy that no current mission can see them. Above them, solar and reactor neutrinos. Higher still, atmospheric and supernova neutrinos. And then, far out beyond the familiar planets on this map, an ultra-high-energy tail stretches into territory almost no one predicts. Here is the looming question. If the low-energy end already shattered expectations, revealing oscillations, mass, and new physics, what happens when a neutrino arrives not with millions or billions of electron volts, but with 1,000,000 billion? Tonight, we're going to follow one of those cosmic beasts as it slams into Earth. And the part that absolutely no one anticipates is where the trail leads next. So when a neutrino arrives carrying 1,000,000 billion electron volts aimed straight at Earth, there's a brutal irony. It is one of the most violent particles the cosmos can hurl at the solar system, and it still almost certainly passes through the entire planet without touching a thing. You can think of neutrinos as bullets, but not normal bullets. Imagine firing a rifle through a cathedral made of fog. The bullet almost never hits a droplet. Walls, floors, people, planets, none of it matters. The neutrino flies on, indifferent, so you can't just put up a wall and wait. You need a target so enormous and timing so exquisite that the rare collision becomes visible at all. This is what physicists mean by a tiny interaction cross-section. Not a physical size, but a probability. If you could stack solid lead from here to a star, a light year of metal, the highest energy neutrinos would still treat it like a suggestion, not a barrier. Even that absurd column of atoms would only stop a fraction. The rest would glide through untouched, as if the entire structure were a ghost. So how do scientists catch a ghost bullet that ignores almost everything? Before we get started with IceCube's radical design, it helps to see how the mission to detect neutrinos began. Earlier experiments turned enormous tanks of water or cleaning fluid into silent cameras. They buried them deep underground, far from the noisy hail of cosmic rays, and lined the walls with photomultiplier tubes, ultra-sensitive light detectors watching for the faintest flash. When a neutrino finally does interact, it kicks an electron or another charged particle to near light speed inside that medium. And then something beautiful happens. The particle outruns light in that material, not faster than light in a vacuum, but faster than light can move through water or liquid. The result is Cherenkov radiation, a sharp blue cone of light, like the optical boom of a superluminal shockwave. Those rare cones were the first photographs of bullets in flight. A single flash, a single track, maybe a few events per day or per month out of trillions upon trillions of neutrinos streaming through. By the end of tonight, you're going to understand why no one expects big numbers here. To see a handful of clean events, detectors must hold thousands of tons of ultra-pure liquid and stare patiently for years. The trade-off is brutal. Higher energy gives a slightly better chance of interaction, but the sources are rarer. So the only winning move is scale. More volume, more time, more silence. Now, let's begin the pattern interrupt. What if the detector is not a tank at all? What if Earth itself becomes part of the instrument? No one predicts using a whole planet as a neutrino filter, but that is exactly the logic behind the next step. Turn the Antarctic ice sheet, kilometers thick, incredibly clear, naturally shielded, into a cubic kilometre lens for Cherenkov light. From that idea, IceCube is born. So how do you turn that idea into hardware? How do you transform a poetic vision of using Earth as a detector into a real instrument that can catch a single ghost particle out of trillions? Tonight, we're going to walk to the end of the world, stand on a frozen desert, and look down through a telescope made of ice. Geographically, IceCube sits at the literal bottom of the planet, the Amundsen Scott South Pole Station. No cities, no trees, just a high, dry plateau of ancient ice, more than 2,800 meters above sea level, bathed in 6 months of daylight and 6 months of night. Under that surface lies some of the clearest natural ice on Earth, compressed and purified over hundreds of thousands of years. That ice is the lens. The South Pole is the mount. Now, let's begin with the scale. IceCube is not a dome, not a dish, not a mirror. It is a three-dimensional grid of more than 5,000 digital optical modules, or DOMs, buried between 1.5 and 2.5 kilometers below the surface. Each DOM is a glass sphere holding a sensitive photomultiplier and electronics. The spheres are strung like beads on 86 vertical cables, then lowered into water-filled boreholes that refreeze around them. When the grid is complete, those strings outline a detector, roughly a cubic kilometre in volume. A 1 kilometre on a side chunk of the Antarctic ice sheet has been wired for light. The Antarctic ice is not just convenient, it is ideal. At those depths it is dark, no sunlight, no bioluminescent life, no city glow. It is transparent, so clear that blue Cherenkov flashes can travel hundreds of meters. It is stable, temperatures well below freezing, no liquid water sloshing, no waves, no weather. And above it, nearly 2 kilometers of overlying ice and atmosphere act as a shield, filtering out much of the background particle noise raining down from space. The result is a quiet, three-dimensional camera, waiting for the rare instant when a neutrino finally collides and launches a charged particle through the ice faster than light travels in that medium. Getting those 86 strings into place is an engineering mission that no one expects to be easy. The team uses a hot water drill to melt narrow shafts more than 2 kilometers deep, working against the clock before they refreeze. Delicate domes must be lowered by the hundreds in temperatures that can plunge below minus 70 degrees Celsius, then survive the pressure as the ice closes around them. Every sphere has to talk to every other sphere, synchronized to nanoseconds, forming a single coherent observatory spread through a volume larger than most skyscraper districts. By the end of tonight, you're going to understand that IceCube is not just a detector, it is a new kind of telescope. Traditional telescopes collect light from stars and planets. Radio dishes collect long wavelength signals from across the solar system and beyond. IceCube collects something stranger, faint, nanosecond-long blue flashes from particle tracks carved in ice when a passing neutrino finally interacts. From the timing and brightness pattern across thousands of DOMs, scientists reconstruct the direction and energy of an invisible visitor that may have crossed billions of light years before striking this frozen boundary. No one predicts that a telescope with no mirror, no lens, and no moving parts can reveal the most violent accelerators in the universe. Yet that is exactly what this buried cube of ice is built to do. And when a neutrino arrives with an energy tens of thousands of times higher than anything CERN's accelerators can reach, this quiet Antarctic camera will be the first to know. To catch a ghost, you have to start by seeing the invisible. IceCube's trick is to turn the silent passage of a neutrino into a flash of blue that screams through the ice. When a neutrino finally does interact, it does not light up the detector directly. It transfers its energy to a charged secondary particle, often a muon, that explodes out of the collision and races through the Antarctic ice. That muon is moving so fast that in this medium it outruns light itself. Not the universal speed limit in vacuum, but the slower speed of light inside the dense crystal lattice. And when a charged particle breaks that local limit, something dramatic happens. Cherenkov radiation is the optical equivalent of a sonic boom. An aircraft that crosses the sound barrier piles up pressure waves into a shock cone. A muon that crosses the light barrier in ice piles up electromagnetic waves into a cone of blue light. The result is a sharp, coherent shock front of photons spreading out behind the particle like a glowing wake behind a speedboat. In a cubic kilometre of clear polar ice, that wake can travel hundreds of meters. Now, let's begin to see how that becomes data. Buried throughout this frozen volume are more than 5,000 digital optical modules. Each DOM is a glass sphere holding a photomultiplier tube and electronics, a self-contained eye that can detect just a handful of photons. With nanosecond precision, it records when each photon hits and how bright the flash was. For a single high-energy muon, dozens, hundreds, sometimes thousands of these eyes will blink in sequence as the Cherenkov cone sweeps past. From above, the pattern would look like a three-dimensional constellation suddenly turning on inside the ice. One string of DOMs brightens in a line, neighbouring strings flicker slightly later. The timing is not random, it is geometry written in light. By the end of tonight, you're going to understand why that geometry is everything. Scientists feed those arrival times and intensities into reconstruction algorithms that run the movie backward. If one DOM on a string lights first, and the next one down lights a few nanoseconds later, the code infers the direction of the muon's track. If DOMs across the array trigger nearly simultaneously, the event is close and bright. From these delays and amplitudes, the system solves for the path, the angle across the sky, the energy deposited, even whether the original neutrino was more likely a muon, electron, or tau flavor. For ultra-high-energy neutrinos, the effect is impossible to miss. No one expects a gentle sparkle. The ice detonates in light. The track can cross the entire detector, with DOMs lighting up like a stadium during a night launch. Compared to the soft background of atmospheric particles, these events stand out like a flare in the dark, a clear signal that something from far beyond the solar system has slammed into this frozen boundary. But seeing the track is only half the mystery. The next question is far more unsettling. Where in the universe did a particle that violent actually come from? To answer that, you have to solve a quieter, more frustrating problem. Most of what IceCube sees is not from deep space at all. High-energy particles from the Sun and distant planets constantly slam into the top of Earth's atmosphere. Those cosmic rays smash into air molecules and create showers of secondary particles, including muons that plunge downward toward the ice. Those muons are fast, charged, and bright. They also produce Cherenkov light, tracing long blue tracks that look a lot like neutrino events. So the first mystery inside this frozen detector is not where did it come from, but is this even a neutrino? If every downward-going flash were accepted as a ghost particle from beyond the solar system, the signal would be buried under an avalanche of atmospheric background. Scientists needed a way to separate the rare from the routine, the cosmic messenger from the local noise. Their solution is almost absurdly elegant. Use Earth itself as part of the instrument. Before we get started with exotic sources and violent galaxies, you have to understand this one move, because it turns the entire planet into a neutrino filter. Cosmic ray muons can only come from above. They are born in the atmosphere, and they don't travel through thousands of kilometers of rock. Neutrinos, on the other hand, barely notice matter at all. Trillions pass through your body every second, so if a track in IceCube appears to rise upward, as if a particle entered from beneath the detector, crossed the array and kept going toward the sky, there is only one realistic explanation. That particle passed through Earth. In this view, the planet becomes a giant shield. The rock, metal and liquid interior block almost every known particle, absorbing ordinary cosmic rays, stopping muons, and quenching the electromagnetic spray from the atmosphere. What survives that journey, what emerges on the far side and interacts in the last few kilometers of ice near the South Pole, is overwhelmingly likely to be a neutrino. Tonight, we're going to treat Earth not just as home, but as part of a solar system-scale detector. By the end of tonight, you're going to understand why an upward-going streak of Cherenkov light can be trusted in a way a downward streak never can. But there is a twist. At low and moderate energies, neutrinos pass through Earth as if it were transparent glass. At ultra-high energies, the ghost particle stops being quite so ghostly. The interaction probability rises. The planet that once looked invisible to them becomes partially opaque, especially along the longest paths through the core. No one expects a solid world to double as both detector and dial, but that's exactly what happens. How likely a neutrino is to appear from a given angle depends on its energy. Fewer survive the deepest crossings. That complexity is not just a nuisance, it encodes information. The pattern of where neutrinos arrive from and where they vanish helps scientists estimate just how extreme their energies really are. Out of millions of events, most are filtered away by this planetary shield. What remains is a tiny, precious set of true cosmic neutrinos. And in 2022, within that purified sample, IceCube saw one track that absolutely no one anticipates. A single ghost particle with a violence that dwarfed every collision ever made at CERN. The universe did not send a warning. Over the South Pole, the sky looked calm. The solar wind whispered past Earth as it always does. At the IceCube Neutrino Observatory, thousands of digital optical modules, DOMs, sat buried in the Antarctic ice, quietly watching a cubic kilometre of frozen darkness. To the few people at the station, it was a normal day in a long mission. No one expects history to arrive as a silent blip in a data stream. Deep below, the detector counted. Tiny flashes, random noise, the endless hail of low-energy particles that never make headlines. Terabytes of signals flowed through cables, through servers, through algorithms trained to ignore almost everything. Tonight, we're going to focus on the moment that system blinked. In less than 1,000th of a second, something changed. A track of Cherenkov light. Those eerie blue shockwaves that appear when a charged particle outruns light speed in ice, cut across a swath of the array. Dozens, then hundreds of DOMs lit up in a precise expanding pattern. The reconstruction software had seen millions of events. This one was different. It was brighter, sharper, violent. No one predicts a ghost particle will announce itself like a flare. Yet, that is exactly what the algorithms saw. They flagged the event, tagged it as unusually energetic and filed it away for human eyes. On the surface, nothing shook. No spacecraft trembled. The planets continued their orbits, but in the data, the universe had just fired a particle cannon at Earth, and IceCube had caught a single round. Weeks later, as scientists combed through the run, the magnitude sank in. The reconstructed energy was on the order of 10 to the 15th to 10 to the 16th electron volts. That is tens of quadrillions of electron volts packed into one neutrino. For comparison, the large Hadron collider smashes protons together at about 10 to the 12th electron volts. This ghost particle carried nearly 30,000 times more energy than the most powerful collisions humans have ever engineered. By the end of tonight, you're going to understand why that number is terrifyingly impressive. Ultra-high energy neutrinos like this do not come from ordinary stars or gentle solar flares. They live firmly beyond the everyday in the regime IceCube was built to explore, the extreme boundary where known physics is pushed by unimaginable engines. Now, let's begin to treat this as a clue. A single, almost massless particle crossed intergalactic space, threaded past galaxies and planets, and still arrived at Earth with more punch than a flagship collider beam. What kind of cosmic catastrophe can accelerate something that small to such ridiculous energies and send it straight at our planet? Somewhere out there, far beyond the solar system, something is not just glowing. It is firing. And this one neutrino is the calling card. That calling card comes with a number stamped on it that almost feels like a misprint. This one neutrino carried roughly 30,000 times the energy released when two protons smashed together inside the large Hadron collider. one ghost particle outmuscling the flagship machine of human high-energy physics. To understand how outrageous that is, you have to appreciate what it takes to make a single LHC collision. The collider is a 27-kilometre ring buried beneath the French-Swiss border, a loop of vacuum pipes so empty that interstellar space starts to sound crowded. Superconducting magnets, cooled to colder than deep space, bend and focus beams of protons as they race around at 99.99999% the speed of light. Each proton in that beam carries on the order of 10 to the 12th electron volts of energy. That is the product of decades of engineering, international funding, and a mission that has redefined particle physics. Now, imagine that carefully tuned, meticulously steered proton finally colliding with another proton. The flash of energy, the spray of exotic particles, the detectors ringing with data. Tonight, we're going to put that beside what just hit Earth from beyond the solar system. This single neutrino, 30,000 times more energetic than one of those proton-proton impacts. No tunnel, no magnets, no power grid. Before we get started with everyday comparisons, lock in the scale. A typical chemical bond in your body or in the air holds about 1 electron volt. Nuclear reactions jump up to millions of electron volts per particle. The LHC pushes that to 1 trillion electron volts. Then this neutrino shows up in the quadrillion to 10 quadrillion range. Chemical to nuclear to collider to ghost particle. Each step a leap of orders of magnitude. The hierarchy is brutal. The universe did not just nudge past the LHC, it sprinted ahead by 4 orders of magnitude. Now, let's begin to translate that into something you can feel. Take a fast-pitched baseball, maybe 90 miles per hour. Its kinetic energy is on the order of tens of joules. Convert that to electron volts and you are in the 10 to the 20th range. The neutrino that IceCube caught is in that same ballpark, only compressed into 1 subatomic point. The energy you expect from a visible, solid object in your hand, focused into a particle that could cross a wall of lead light years, thick without noticing. By the end of tonight, you're going to understand why this comparison is so unsettling. No one expects a single particle to rival a macroscopic object. No one predicts that the same universe that gently blows solar wind past the planets will also hurl a microscopic projectile with the punch of a baseball, straight through our cosmic neighborhood. And absolutely no one anticipates how extreme the engine must be to launch it. Because if 1 neutrino can carry that much energy, what kind of accelerator is hiding out there in the dark, and what else might it be firing that we have not yet seen? To answer that, scientists do something almost cinematic. They replay the impact, not in space, not at the source, but inside a block of Antarctic ice. Tonight, we're going to step into that replay, into a 3D map, where a ghost particle leaves the only evidence it ever existed. Before we get started, picture IceCube not as a buried machine, but as a transparent cube of crystal, a kilometre on a side, hanging in the dark. Inside this cube, every digital optical module, every DOM, becomes a sphere in a virtual model. Thousands of spheres suspended in a grid. Their colours mark time, their sizes mark brightness. 1 quiet second, the map is empty. The next, it erupts. For the 2022 event, that eruption is not a messy splash. It is a line, a long, bright track, cutting through a huge fraction of the detector like a glowing wire threaded through glass. That line is not the neutrino itself. No one expects to ever see the neutrino. What the DOMs record is the muon it creates when it finally slams into an atomic nucleus in or near the array. The muon is the stand-in, the tracer particle. It races through the ice faster than light can move in that medium, launching a cone of Cherenkov light, a pale blue shockwave. DOMs along its path flare in sequence. In the event display, early hits might glow in deep reds, then oranges, then greens and blues as time ticks forward. Larger spheres mean more photons, smaller ones, fewer. Instantly, the human eye sees what the raw numbers conceal: direction, structure, intent. Now, let's begin to read that intent the way scientists do. They take every lit DOM, every recorded timestamp, and fit a line through the 3D pattern. The earliest flashes anchor one end, the latest hits anchor the other. Prediction meets observation as algorithms nudge that line until the timing of the Cherenkov wavefront matches the data within nanoseconds. Follow that fitted line backward, out of the ice, past the South Pole, and it points to a location on the sky where the neutrino must have come from, far beyond the solar system. But direction is only half the story. The total light yield, summed over thousands of DOMs, and the sheer length of the track through the array scale with the muon's energy, and therefore with the neutrinos. A short, faint streak means a modest impact. This event is neither short nor faint. It blazes. From that blaze, scientists infer an energy tens of quadrillions of electron volts, roughly 30,000 times what the most powerful human-built accelerator can deliver. By the end of tonight, you're going to understand that this single glowing line is more than a pretty visualization. It is a fingerprint, a fossil track etched in ice by a particle that may have crossed intergalactic space for billions of years, slipped past planets and stars, and finally, at random, chose 1 cubic kilometre of Earth to reveal that it was ever there. That fossil track in the ice does one more astonishing thing. It points. When a neutrino, this energetic, slams into the Antarctic ice, it creates a secondary particle that streaks through the detector faster than light can move in that medium, lighting up the optical sensors in a precise sequence. From the timing and brightness of those tiny flashes, scientists reconstruct a straight line, a track that shows where the particle came from and where it was headed. It is the cosmic equivalent of rewinding a bullet's path through space. Now, let's begin with a crucial idea: angular resolution. Telescopes have it. Cameras have it. IceCube has it too, but instead of sharp images of planets, it measures how finely it can trace that glowing line back across the sky. For long, clean tracks, the angular resolution can be better than a fraction of a degree, comparable to picking out a coin from kilometres away. For messier events, it's a bit worse. The 2022 ghost particle produced a track good enough that its direction was not a vague smear. It was a narrow arrow. But in space, nothing is ever perfectly sharp. Every reconstruction comes with uncertainty, a small but real wobble in the angle. So on the sky, this neutrino does not correspond to a single pinprick. It becomes an uncertainty cone, a thin, three-dimensional wedge extending out from Earth, which, when projected onto the celestial sphere, turns into a patch of sky. Not the whole sky. A tiny island on the cosmic ocean, maybe a few tenths of a degree across, where the true source almost certainly hides. That patch is where the real hunt begins. Tonight, we're going to follow what scientists do next. They take that cone, convert it into coordinates on the sky, and plot it on detailed celestial maps. Then they layer on catalogues, nearby galaxies, distant quasars, blazing blazars whose jets aim toward the solar system, and active galactic nuclei powered by supermassive black holes. Each point on the map is a potential extreme accelerator, a place where magnetic fields and relativistic jets might fling particles to energies that make CERN's most powerful collisions look modest. For this event, the arrow landed in a crowded neighborhood. The direction pointed toward a region rich in active galaxies and high-energy emitters, places where the cosmic wind is anything but gentle. No one expects a clean, isolated culprit. No one predicts that a single map overlay will shout the answer. Instead, absolutely no one anticipates how tantalizing it feels to see several prime suspects sitting right inside that cone. Somewhere in that small patch of sky, a hidden engine hurled a ghost particle across intergalactic space and straight at Earth. By the end of tonight, you're going to understand how that vague island on the map turns into a test of competing ideas about the most extreme accelerators in the universe, and why the next step is to watch that region with every instrument we have. That vague island on the map is not empty. It's crowded with engines, not the tidy, human-made rings of CERN, but titanic machines carved out of gravity, magnetic fields, and falling matter. Tonight, we're going to walk straight into one of those engines and see how a black hole turns into a particle collider. At the heart of many galaxies, including our own, sits a supermassive black hole surrounded with gas, dust, and the occasional disrupted star, and something extraordinary happens. Infalling material doesn't plunge straight in, it spirals, forming a blazing accretion disk where friction heats matter to millions of degrees. Around that disk, magnetic fields twist and buckle. Under the right conditions, they launch narrow, oppositely directed jets of particles that can punch out of the galaxy and into intergalactic space. These are active galactic nuclei, AGN. From far away, they look like compact, overachieving points of light, outshining all the stars in their host galaxies. Up close, they are laboratories where gravity's pull, rotation, and magnetic tension combine to fling particles to energies that make our most ambitious mission hardware look modest. No one expects gentle behavior near a supermassive black hole. The surprise is just how organized the violence becomes. Inside those jets, magnetic fields act like rails and shock waves act like hammer blows. Protons and heavier nuclei get trapped, scattered back and forth across shocks, and whipped along magnetic lines. Each crossing adds energy, over and over, until a single proton can carry more energy than a fast-pitched baseball. For comparison, the Large Hadron Collider throws protons together at around 10 norm or 12 electron volts. In these cosmic accelerators, nature routinely reaches 10 Wol 15, 10 Wol 18, and beyond. Now, let's begin to narrow the suspects. There is a special subclass of AGN called blazars. Here the geometry does something dramatic. One of those relativistic jets is pointed almost directly at Earth. That alignment concentrates the radiation like a cosmic spotlight. The result is an object that flares, brightens, and fades across radio, optical, X-ray, and gamma-ray wavelengths, sometimes changing within hours. From our perspective inside the solar system, a blazar is less a distant galaxy and more a fire hose aimed straight at the detectors. When those ultra-high-energy protons plow through the intense light fields around the accretion disk or collide with stray gas in the system, they don't just keep going, they interact. They produce short-lived particles called pions. Charged pions decay into muons and then into neutrinos. Neutral pions decay into gamma rays. So, a single violent interaction in a jet can launch a paired signal, a burst of high-energy light, and a ghost particle that ignores almost everything. Before we get started on eliminating suspects, connect this back to that cone on the sky. In the error region of the 2022 event, catalogues light up with AGN and blazar candidates, compact radio sources, variable gamma-ray emitters, known active nuclei. No one predicts a clean smoking gun yet. But absolutely no one anticipates that so many natural colliders could hide in one patch of sky without leaving more clues. The question is, which of these engines flared at exactly the right moment to fire a neutrino 30,000 times stronger than CERN straight at Earth, and what else was launched with it that we still haven't seen? So, if it wasn't a blazar, what was powerful enough to hurl a ghost particle with 30,000 times CERN's energy straight through the solar system? To even have a chance, you need something that makes a blazar look restrained. That's where gamma-ray bursts enter the lineup. Gamma-ray bursts, or GRBs, are the most luminous electromagnetic explosions known. For a few furious seconds, a single burst can outshine every star in its host galaxy combined. Scientists think most long GRBs come from collapsing massive stars that die in hyper-energetic supernovae, while short GRBs are linked to neutron star mergers that twist space with gravitational waves. Tonight, we're going to stand next to those engines in imagination and ask, could one of them have fired this neutrino at Earth? The basic picture is extreme. A massive star's core collapses into a black hole, or two neutron stars collide. Relativistic jets punch out along the poles at nearly light speed. Shocks form in those jets, magnetic fields knot and whip, and particles get flung to energies far beyond anything a human-built mission can reach. The same violent processes that generate blinding gamma rays can also smash protons into surrounding matter and radiation, creating pions that decay into ultra-high energy neutrinos. Here's the pattern interrupt. From Earth's distance, a GRB is just a brief flash on a detector, maybe a few tens of seconds long. But inside that flash, in a volume smaller than a planet, the energy flow can rival what the Sun emits over its entire 10 billion-year lifetime. No one expects jets like that to be tidy. They are natural particle colliders, with dense radiation fields and shock fronts acting as accelerators, targets, and beam dumps all at once. GRBs are not the only suspects. Starburst galaxies packed with rapid star formation and frequent supernovae create large-scale shocks where cosmic rays can be boosted again and again. Magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, can crack their own crusts, releasing flares that saturate gamma-ray instruments. Even clusters of galaxies where entire swarms of galaxies swim in hot plasma host colossal shocks, driven by mergers and the combined wind of countless active nuclei. Each of these environments can, in principle, launch neutrinos that cruise far beyond the boundary of their home system. To sort them out, scientists lean on multi-messenger astronomy. Now, let's begin with the detective work. Neutrino events from IceCube are compared with gamma-ray and X-ray satellites, with optical telescopes scanning for supernovae, and with gravitational wave observatories listening for mergers. By the end of tonight, you're going to understand why timing and direction are everything. If a neutrino, a gamma-ray flash, and a space-time ripple all point to the same place at the same moment, the case is nearly closed. So did the 2022 neutrino line up with any known burst or flare? No one predicts a simple answer. So far, there is no clear GRB, no obvious magnetar outburst, no dramatic cluster merger recorded at just the right instant. That absence may be the most intriguing clue of all. It hints that there could be a hidden class of cosmic engines, choked jets, buried accelerators, or dark outflows that light up in neutrinos while staying almost invisible in every other channel. The next step is to push the detectors and the sky maps hard enough to catch one of those engines in the act. So why does this one ghost particle matter so much when the detector is lighting up all the time? Tonight, we're going to zoom out from that single streak of blue light in Antarctic ice and look at the ocean of noise it had to rise above. Before we get started, picture what IceCube actually sees. Buried in a cubic kilometre of clear Antarctic ice, more than 5,000 optical sensors stare into the dark. Every year, they record millions of events, not dozens, not thousands, millions. Almost all of them are the debris of other cosmic intruders. High-energy protons and nuclei slam into the top of Earth's atmosphere, create showers of particles, and those showers rain down muons and atmospheric neutrinos that plunge through the detector. From IceCube's point of view, this is the weather. A constant hail of particles from the sky driven by the solar wind, galactic rays, and the changing mood of our star. The mission is not to count the hailstones. The mission is to find the single snowflake that came from beyond the solar system without melting in the storm. Only a tiny fraction of the signals are astrophysical neutrinos born outside the solar system in distant galaxies, near violent planets' remnants, black holes, or jets that punch past any ordinary boundary. And within that already tiny set, only an even smaller subset reach ultra-high energies tens of thousands of times beyond what CERN's large Hadron Collider can achieve. No one predicts those will be common. Absolutely no one anticipates catching one with a clean, sharp track and a well-defined direction. That rarity is the point. When an ultra-high-energy neutrino hits, it is not just another data point. It is a direct probe of conditions so extreme that no spacecraft, no collider, and no laboratory experiment can reproduce them. One particle with one measured energy and one incoming direction can rule out entire families of models for how cosmic accelerators work. Its energy tells scientists how powerful the engine must be. Its direction on the sky, reconstructed from the faint Cherenkov light in the ice, tells them where to look for the hidden source. Together, energy and direction become a kind of cosmic fingerprint. With that fingerprint, theorists can test how particles are accelerated in active galactic nuclei, how they interact with background radiation across intergalactic space, and whether new physics appears at energies far beyond any human-built machine. By the end of tonight, you're going to understand that in neutrino astronomy, quantity is not the same as quality. A single, clean, ultra-high energy event can be as valuable as years of lower energy observations. Millions of atmospheric hits map the background. One ghost particle from deep space redraws the map, and the next step is to ask, if one neutrino can do this much, what happens when we start catching them by the dozens? So if one ghost particle can redraw the map, the next question is, where did this one begin its journey? To answer that, you have to leave the solar system behind and drop into one of the most violent engines in the universe. Tonight, we're going to ride that particle from birth to impact. Now, let's begin. Picture a supermassive black hole at the heart of a distant galaxy, millions or billions of light years beyond the Milky Way. Around it, a swirling disk of gas and dust funnels inward, while twin jets of plasma lance out at nearly the speed of light. In those jets, magnetic fields twist like coiled steel cables. A lone proton is trapped there, spiraling along those field lines, whipped around again and again. Each orbit, it steals a little more energy from the magnetic wind. Not once, Not 1,000 times, but over countless loops, shock waves, and turbulence act like a cosmic particle accelerator far beyond anything scientists can build on Earth. The proton climbs to energies that make CERN's collisions look modest. Then comes the crucial moment. The proton slams into a stray photon from the jet's intense radiation field. Expectation. The photon just passes through. Reality. At these extreme energies, the collision has enough punch to rearrange matter itself. Out of that impact pops a short-lived pion, a heavier cousin of the electron. In less than a trillionth of a second, the pion decays, spitting out a neutrino and other fragments. The neutrino is born already moving at essentially light speed, carrying a staggering amount of energy in a particle that almost never interacts. At first, it has to escape. It threads its way through dense plasma, through clouds of hot gas, through tangled magnetic fields that would trap charged particles for ages. Photons are scattered, absorbed, re-emitted. Protons are bent and caged by the magnetic boundary of the jet. The neutrino ignores all of it. No charge, almost no mass. No one predicts how cleanly it slips through the chaos. Then it is out, in the vast dark between galaxies. For millions, maybe billions of years, it crosses intergalactic space. It passes the faint halos of distant galaxies, skims the outskirts of star systems, cuts through invisible rivers of dark matter and thin gas. It flies through the orbits of planets, through the blazing atmospheres of stars, through entire worlds as if they were not there. Trillions of neutrinos do this every second, but this one carries 30,000 times the energy of a proton collision at the Large Hadron Collider. One day, if you can even call it a day after such a journey, it reaches a small yellow star with a thin bubble of solar wind around it. It plunges through that boundary, crosses the orbits of the outer planets, and heads straight for a rocky world wrapped in a thin atmosphere and a shell of ice at one pole. It passes through the crust, mantle, and core of Earth as though the planet were smoke. Almost every neutrino would leave without a trace, but absolutely no one anticipates which nucleus will, by pure chance, be in the wrong place at the right time. Deep under the Antarctic surface, in a cubic kilometre of ancient ice wired with thousands of silent sensors, a single atomic nucleus finally says enough, and the ghost slams into reality. The result is a flash of blue light that turns a billion-year journey into one line on a screen, and that line is about to reveal where in space this impossible mission began. That one blue flash in Antarctic ice is more than a detection, it's a comparison. On one side, there is the Large Hadron Collider, a 27-kilometre ring buried under the French-Swiss border, magnets cooled near absolute zero, beams of protons guided and focused with exquisite precision. Every collision is planned, timed, and catalogued. By the end of tonight, you're going to understand just how controlled that environment really is. On the other side, there is a black hole's accretion disk or the shock front of an exploding star. No vacuum chambers, no safety interlocks. Just magnetic fields twisting space, jets punching through gas, and particles whipped to energies no human mission can touch. Where the LHC nudges protons to a fraction of light speed, these regions hurl them there and then keep going. The contrast is brutal. In Geneva, scientists spend years aligning beams so they cross at a point smaller than a grain of sand. Near a spinning supermassive black hole, turbulence, radiation, and chaos collide in a way no one expects and no one controls. Yet out of that violence come neutrinos and cosmic rays with energies tens of thousands of times higher than anything in the solar system's most advanced collider. Colliders give something nature does not: repeatability. Fire the same beams, record the same distributions, tease out tiny deviations from theory. That's how the Higgs boson was discovered, how the Standard Model was nailed down to absurd precision. Those rings and tunnels are where unknown particles can be produced on demand again and again, until their properties are mapped. But the universe offers something colliders cannot realistically provide on Earth: raw energy scale. That single neutrino, 30,000 times stronger than CERN's best shot, is a probe of physics at center of mass energies beyond any planned machine. Each ultra-high energy cosmic ray that slams into the atmosphere turns the sky into a temporary detector, a natural experiment running at energies engineers can only simulate. This is where the story shifts. Pattern interrupt. The most powerful accelerator humanity will ever use might not be a bigger ring. It might be software wrapped around detectors like IceCube, the Pierre Auger Observatory, and future space-based missions, decoding what the cosmos is already doing for free. With these extreme messengers, scientists can test Lorentz invariance by asking whether particles at unimaginable energies still obey the same speed limits and transformation rules. They can search for signs of new physics in how these neutrinos scatter, or fail to scatter, off Antarctic ice. They can constrain dark matter models by looking for excesses, deficits, or strange arrival directions that no conventional accelerator beam could ever reproduce. Tonight, we're going to treat the entire universe as a laboratory. Before we get started on where this particular ghost came from, one question hangs over every future collider proposal. In the long run, will the most powerful particle experiments be built in tunnels under Earth, or in algorithms and observatories listening to the violent wind of space beyond our solar system's boundary? To turn the entire universe into a particle accelerator, there is one brutal constraint. The universe does not send many tickets. At the very highest energies, the flux of ghost particles is almost zero, not zero in principle, but so low that for practical purposes you could wait a lifetime and never see one. By the end of tonight, you're going to understand just how absurd that rarity really is. Current estimates say that for neutrinos at these ultra-high energies, only a few pass through an area the size of a square kilometre each year. Not a few per second, a few per year. Imagine drawing a 1 kilometre by 1 kilometre box on the Antarctic ice and then sitting there, in the dark, waiting for a handful of invisible bullets that almost never hit anything. Now, let's begin to scale that down to what IceCube actually sees. The detector effectively watches a cubic kilometre of crystal clear ice. That sounds huge, but neutrinos are infamous for ignoring matter. Trillions pass through your body every second without leaving a trace. So even when the entire solar system is bathed in a cosmic wind of particles from distant galaxies, only a vanishing fraction will interact inside that single frozen volume. To feel the odds, shrink the problem into something familiar. Picture an enormous beach with mountains of sand stretching for kilometers. The flux of ultra-high energy neutrinos is like waiting for one specific grain from one specific bucket to land on a single square meter of that beach sometime this year. Not any grain, one particular grain with an ID tag. Or imagine a swimming pool in a torrential rainstorm, taking in millions of drops. Catching a neutrino like this is the equivalent of demanding one exact raindrop from one exact cloud to hit one exact tile on the bottom. No one expects an event that rare to show up clearly in the data. No one predicts that out of the constant hiss of lower energy particles and atmospheric background, a single track will scream, "I came from beyond the galaxy." Yet that is precisely what these ultra-high energy detections look like when they appear. They carve a sharp, bright line of Cherenkov light through the ice, a geometric wound that stands out against the softer spray of more ordinary events. The challenge for scientists is proving that this is not just a weird fluctuation from more mundane sources. Atmospheric neutrinos, born when cosmic rays hit the air above the planets, are constantly raining through the detector. Statistical analyses compare the direction, energy, and timing of each event against detailed models of that atmospheric background. When an event sits far out on the tail of those distributions, with an energy far beyond what the atmosphere can plausibly produce, the odds of it being a random imposter plunge. At that point, the universe is doing something that absolutely no one anticipates at first glance. A single data point becomes a shout in a whispering crowd, a sharp spike in a sea of noise. When that happens inside IceCube's cubic kilometre, scientists stop, rewind, and dissect every photon. Because if space can send one such messenger through our solar system, the next question practically demands itself: where exactly did that ghost come from? So when that single ghost particle lights up IceCube's frozen lattice, it is not just an odd event log entry. It is a new way of looking at the universe switching on for a brief, blinding instant. Tonight, we're going to treat that flash as more than a curiosity. We're going to treat it as part of a whole new kind of telescope. Neutrino astronomy is exactly that, using neutrinos instead of light to map and study the most violent engines in space. Traditional astronomy leans on photons, from radio waves to gamma rays, to sketch the solar system, the Milky Way, and the cosmos beyond. But photons have a problem. They are social. They interact. They get pushed around. Before we get started on why neutrinos change the game, it helps to see how limited light really is. Photons can be absorbed by dust clouds scattered by gas, or blocked outright by dense stellar nurseries and the hearts of galaxies. The most energetic gamma rays, the ones that should trace the fiercest particle accelerators, collide with background light and matter long before they can cross cosmological distances. On paper, they should reach us. In practice, the universe sands them down. Neutrinos are the opposite. They barely notice matter at all. Trillions pass through your body every second through Earth, through planets and spacecraft, without leaving a mark. That weakness is their strength. When a high-energy neutrino escapes from the dense core of a blazar, or the shock front of a gamma-ray burst, it travels in almost a perfectly straight line, ignoring magnetic fields and the tangled wind of charged particles. It points back to its source like an arrow. This means neutrino astronomy does something no optical or gamma-ray telescope can do. It lets scientists see directly into the central engines of cosmic accelerators, the regions where light is trapped, choked, or erased. By the end of tonight, you're going to understand why a single track in Antarctic ice can tell more about those hidden regions than an entire image of a galaxy. The first hints came in the past decade when IceCube events lined up suspiciously well with flaring blazars, galaxies whose central black holes fire jets straight at Earth. Correlations between neutrino detections and outbursts in gamma rays nudged models of where the highest energy cosmic rays are born. Some candidate sources survived, others did not. Prediction met observation, and whole families of theories about cosmic ray origins were quietly retired. The 2022 ultra-high energy event, 30,000 times stronger than CERN's collisions, slots into this growing pattern. It is one point in a slowly thickening constellation of ghostly hits, a catalogue that will, over time, become a neutrino sky map of the extreme universe. No one predicts that a cubic kilometre of ice at the bottom of the world will redraw the atlas of violent space, and absolutely no one anticipates the next twist. What happens when those neutrino maps disagree with everything the photon-based universe has been telling us? When those neutrino maps clash with the photon universe, something radical has to happen. Either the models are wrong, or the cosmos is hiding an entire layer of the story. Tonight, we're going to watch scientists try to reconcile those two narratives in real time. The tool for that is multi-messenger astronomy. Instead of trusting just one signal, the new rule is never believe a single messenger when the universe can send four. Light, neutrinos, charged cosmic rays, and even gravitational waves all carry different pieces of the same violent events. Put them together, and you don't just see an explosion in space, you start to understand the engine driving it. So when IceCube flags a monster like the 2022 event, the detector does not sit quietly on some Antarctic server. Within seconds, automated software reconstructs the direction of the incoming track and fires an alert out to the astronomy community. Coordinates, estimated energy, uncertainty region, timestamp. A ghost particle pings the ice and telescopes across the planet snap to attention. This is where the mission turns into a global relay race. Spacecraft in orbit swing their X-ray and gamma-ray eyes toward the patch of sky. Ground-based Cherenkov telescopes check for very high-energy gamma rays. Radio arrays listen for a new jet turning on. Optical observatories scan for a flare that wasn't there the night before, designed for their own targets and schedules. Now, for a few crucial hours or days, they all answer to a single neutrino. The strategy is deceptively simple. Look for coincidences. Did any known blazar brighten in gamma rays from that direction? Did a gamma ray burst trigger within minutes or hours of the neutrino's arrival? Did X-ray monitors or radio surveys catch a transient switching on in that same error circle? The boundary conditions are tight. Same patch of sky, overlapping time window, consistent energy scale. If multiple messengers line up, the odds of a random overlap plunge. This method is not hypothetical. In 2017, a high-energy IceCube neutrino, IceCube 170922A, arrived from a direction that matched a flaring blazar called TXS 0506 + 056. Fermi and Magic saw the blazar in gamma rays. Optical and radio telescopes confirmed it was in an active state. Designed as separate missions to study high-energy space, they converged on one violent galaxy. By the end of tonight, you're going to understand why that single association was hailed as the first solid evidence that blazars accelerate cosmic rays beyond anything in the solar system. Pattern interrupt. Now add gravity. Since 2015, LIGO and Virgo have been catching ripples in space-time from colliding black holes and neutron stars. Every time a big gravitational wave alert goes out, IceCube checks its data. Did any neutrino arrive from that region within that time? A joint hit would reveal not just where the boundary was torn, but how energy and matter were flung beyond it. For the 2022 ultra-high energy ghost, that detective work is still unfolding. Teams have combed through gamma-ray catalogues, blazar monitoring programs, X-ray archives, and gravitational wave event lists, looking for that satisfying snap of puzzle pieces locking together. So far, No one expects a perfectly neat answer. No one predicts that one neutrino will single-handedly rewrite the atlas of extreme space. And absolutely no one anticipates what happens if the final verdict is no counterpart at all. Because that would mean something out there can hurl a particle 30,000 times stronger than CERN and leave almost no other trace in the visible universe. So if there's no bright flare, no screaming galaxy, no obvious engine, what's left? Tonight, we're going to walk right up to the edge of known physics, look over the boundary, and ask whether this ghost particle hints at something even stranger than black holes and exploding stars. The leading suspects stay on the table. Blazing active galactic nuclei, gamma-ray bursts, extreme shock fronts in distant galaxies. They fit comfortably inside the standard model, powered by magnetic fields and charged particles whipping through space at nearly light speed. But in the background, some scientists have been quietly asking a more unsettling question. What if part of the neutrino's sky is coming from new physics entirely, from engines that no current spacecraft could ever see directly? One idea points to dark matter. Not the mild, slow halo that keeps galaxies bound together, but hypothetical, super-heavy dark matter particles, 1 trillion times heavier than a proton, or more. If those relics from the earliest fractions of a second after the Big Bang are unstable, their rare decays could spray out cascades of familiar particles, including ultra-high energy neutrinos that drift through the solar system like silent messengers from the infant universe. Another idea reaches even deeper. Topological defects, cosmic strings, monopoles and domain walls, wrinkles in space-time that might have been woven into the fabric of the cosmos during phase transitions in the early universe. When these defects interact, reconnect, or annihilate, they could dump enormous energy into a tiny region, launching particle jets that make the Large Hadron Collider look like a toy. No one expects these events to be common. No one predicts they would show up in every data set. But if they exist, they are exactly the kind of engines that could hurl neutrinos to energies 30,000 times beyond our best machines. By the end of tonight, you're going to understand why these ideas are exciting and why they're also tightly chained to the data. IceCube doesn't just count hits, it maps their energies and arrival directions across the sky. If super-heavy dark matter in the Milky Way halo were doing most of the work, the neutrino's sky would glow more brightly toward the galactic center. If topological defects were dominant, the spectrum at the highest energies would tilt and curve in very specific ways. So far, that hasn't happened. The observed spectrum looks broadly consistent with a population of distant astrophysical accelerators, and the arrival directions are nearly isotropic, with only subtle hints of clustering. Those patterns place hard limits on how much room there is for exotic contributions. The door is not closed, but it is narrowed. This is the balance point of modern high-energy astrophysics. Speculation is not forbidden. It is invited, but only to the extent that the data will host it. Extraordinary claims require extraordinary evidence, and right now, conventional engines in extreme galaxies can still explain what has been discovered. Now, let's begin to imagine the next step. As IceCube runs longer and as future detectors sprawl across larger volumes of ice and water, the number of ultra-high energy events will climb. Patterns might emerge. A strange excess from one region of space, a sharp kink in the spectrum, a population that turns on only beyond a certain energy. Absolutely no one anticipates rewriting the standard model on the basis of a single neutrino. But a decade from now, a whole new map of the invisible universe might leave scientists with no other choice. The universe is not just throwing neutrinos at Earth, at these energies. It is throwing a challenge at physics itself. Tonight, we're going to ride right along that edge where a single ghost particle can embarrass the most powerful machines humans have ever built. In a collider like CERN's Large Hadron Collider, protons smash together with energies of about 1 trillion electron volts. That sounds enormous until a neutrino arrives with 30,000 times more energy, fired across cosmological space by some distant accelerator near a violent galaxy. At that point, every tiny imperfection in our theories is magnified. A microscopic deviation from special relativity, a whisper of a new interaction, could compound over millions or billions of light years into a measurable delay, a subtle bend, a missing event in the detector. This is where timing becomes a weapon. When a flaring blazar or a gamma ray burst lights up the sky, spacecraft watch the photons while IceCube listens for neutrinos from the same region. By the end of tonight, you're going to understand why scientists obsess over which messenger arrives first and with what energy. If neutrinos and photons leave the same cosmic explosion and cross the same vacuum, they are supposed to reach us at the same speed, limited by the same cosmic speed limit. A difference of even a few seconds, when stretched over billions of years of travel, would be a red flag that the vacuum of space is not as simple as Einstein's equations say. So researchers comb the data for energy-dependent dispersion, the idea that higher energy particles might travel slightly faster or slower than lower energy ones. They search for Lorentz invariance violation, where the laws of physics might subtly depend on direction or speed through the universe, breaking one of the most sacred symmetries in modern physics. They look for unexpected absorption patterns, energies where neutrinos should sail through the cosmic web, but instead vanish, as if space itself is hiding a new kind of fog. The mere fact that a neutrino can survive the journey at these energies is already a constraint. If space-time became wildly foamy or grainy near the Planck scale, if exotic defects or mini black holes riddled the vacuum, ultra-high energy neutrinos would scatter, lose energy, or disappear long before reaching our solar system. Their detection tells scientists that, up to astonishing energies, the smooth space-time of general relativity still holds, and that many speculative models of quantum gravity are already squeezed into a shrinking corner. No one expects a single event to overthrow a century of physics. No one predicts that one ghost particle will shout louder than all the data from colliders and spacecraft. But each ultra-high-energy neutrino tightens the net, closing off entire families of theories, forcing new ideas to thread an ever narrower boundary between what is allowed and what is already ruled out. And yet, hidden in that narrowing gap, there is still room for a surprise so radical that when the next extreme event arrives, absolutely no one anticipates what its trajectory will reveal about the engine that launched it. That narrowing gap is where theory lives. But IceCube does not live in theory, it lives in ice. 2.5 kilometers under the South Pole, that ice looks perfectly clear in diagrams. A pristine cubic kilometre, a frozen cathedral of space waiting for ghost particles to leave blue tracks of light. In reality, the cathedral has scars. Ancient storms, volcanic eruptions, and shifting climate have left thin, invisible layers of dust and bubbles. Each layer bends, scatters, and absorbs light in a slightly different way, turning a simple straight-line reconstruction into a three-dimensional optical maze. For scientists trying to understand a single neutrino, that maze is everything. Light from the muon streaking through the ice does not just travel. It diffuses, it delays, it gets preferentially swallowed at some wavelengths and not others. A photon born near one sensor might arrive late to another or never arrive at all. If those delays are not modelled with painful precision, a trillion electron-volt track can be misread as something dimmer, slower, or coming from the wrong direction. So, before we get started on interpreting a 30,000 times CERN event, the mission quietly turns inward. IceCube spends enormous effort not on the cosmos beyond, but on the medium beneath its feet. Engineers fire calibrated light sources, LED flashes and lasers through the detector like lighthouses pulsing through frozen seas. By the end of tonight, you're going to understand that those flashes are as important as the neutrinos themselves. Each pulse maps how the ice actually behaves, depth by depth, layer by layer, building a living 3D model of optical properties that is constantly refined as more data comes in. Then there is the noise. The boundary between signal and background is not drawn by hand, it is carved out of chaos. Every photomultiplier in IceCube, those glass spheres watching the darkness, has dark noise, random electron hiccups that mimic tiny flashes of light. Above the detector, the atmosphere is raining down muons created by cosmic rays slamming into the air. Thousands of those charged particles plough through the ice every second, far outnumbering the rare neutrino events scientists actually care about. Now, let's begin to appreciate how extreme filtering has to be. Sophisticated algorithms look for coherent patterns in space and time, rejecting isolated blips and downward-going tracks that scream atmospheric. They cross-check geometry, timing, and brightness to decide whether a candidate is a local intruder or a messenger from beyond the solar system. Even then, no one expects perfection. Every reconstructed event carries error bars, a cone of possible directions on the sky, a range of possible energies. For the 2022 neutrino, those uncertainties are carefully quantified. Its direction is pinned down to a small patch of sky, not a single point. Its energy has margins, not an exact integer. But here is the pattern interrupt. When a track is this bright, this long and this clean, the ambiguity shrinks. The event towers above the background. Algorithms, calibration, and ice models all converge on the same conclusion. Despite the layered ice, despite the dark noise, despite the atmospheric muon wind, this particle is robustly ultra-high energy and astrophysical in origin. The universe lit up the Antarctic ice with a single colossal neutrino. And now the question is, which engine among the planets and galaxies out there had the power to launch it straight at Earth? The universe lit up the Antarctic ice with a single colossal neutrino. But that flash in IceCube is only one pixel in a much larger cosmic camera that is just starting to come online. Tonight, we're going to pull back from the South Pole and see how that one detector is becoming part of a global mission to listen to ghost particles from every direction in space. IceCube uses ice. Other teams chose water. Deep under the Mediterranean, scientists built Antares, and now its successor, KM3net, anchoring strings of light sensors in the dark sea between the continents. Far to the north, in the oldest lake on the planet, Baikal GVD is rising through the clear, frigid water of Lake Baikal. Different oceans, different engineering, the same invisible visitors. The principle is identical. A neutrino slams into water, launches a charged particle faster than light can move through that medium, and a cone of Cherenkov light fans out. But the details matter. Water is warmer, more dynamic, filled with bioluminescence, currents, and tiny particles. Ice is stable, layered, incredibly clear. That contrast lets detectors cross-check each other, and it lets them see different slices of the neutrino sky. Here's the trick. Because Earth itself is the shield, every detector sees different directions best. IceCube at the South Pole is perfect for watching neutrinos that have crossed the entire planet from the northern sky. KM3 net in the Mediterranean stares through Earth at the southern sky and the crowded heart of the Milky Way. Baikal GVD fills in high northern latitudes. No one expects a single observatory to capture every event. Together, they begin to act like one giant rotating eye. Energy matters too. Some arrays are tuned for the steady rain of lower-energy neutrinos from the solar system, the atmosphere, and nearby galaxies. Others, like IceCube, are optimized for the rare, ultra-high-energy outliers that carry news from the most extreme engines beyond our galaxy. When one detector sees a burst, the others can check their data for coincident flashes, sharpening the direction and testing the models of where that neutrino came from. And this network is about to get louder. IceCube Gen 2 is on the drawing board. More strings, more sensors, spread over a vastly larger volume of Antarctic ice. The same boundary-breaking technique, but scaled up so far that ultra-high-energy events that were once in a decade could become several per year. By the end of tonight, you're going to understand that this is how neutrino astronomy turns from rare fireworks into continuous monitoring. Beyond even that, scientists are planning to listen in a new way. At energies far above this ghost particle, neutrino impacts can launch brief radio pulses through ice, or even the lunar regolith, a phenomenon called the Ascarian effect. Arrays of radio antennas on the Antarctic surface, balloons drifting in the polar wind, and spacecraft staring at the moon could detect neutrinos with energies no accelerator on Earth will ever reach. Now, let's begin to imagine the end state. Antares and KM3 net in the Mediterranean, Baikal GVD in Siberia, IceCube and its radio cousins at the poles, future detectors in the deep Pacific, on the seafloor, even orbiting above the moon. No one predicts the final map, and absolutely no one anticipates how detailed it will become. But the direction is clear. Earth ringed with neutrino observatories woven into a true multi-messenger listening post where light, gravitational waves, charged particles, and ghost particles are all read together, revealing which planets, stars, and galaxies out there are powerful enough to launch the next impossible neutrino straight at us. That vision of Earth as a multi-messenger listening post is powerful, but it hides an even stranger question. What would the universe look like if ghost particles were not ghosts at all? Tonight, we're going to flip the lights in space, not from darkness to starlight, but from photons to neutrinos. Before we get started, picture walking outside on a clear night and looking up. The familiar constellations are there in visible light. Orion, the Big Dipper, the Milky Way smeared across the sky. Now, let's begin to peel that away. Turn off every photon your eyes can see. Replace them with neutrino light. Instantly, most of those bright stars fade to a dull, uniform glow. The Sun, which dominates the solar system in visible light, becomes just one modest neutrino bulb among many. In this new spectrum, the quiet, middle-aged stars that anchor our constellations are no longer the main event. Instead, a few distant points ignite. Active galactic nuclei, where supermassive black holes feed on infalling gas, blaze like cosmic searchlights. Blazars, with their relativistic jets pointed nearly straight at Earth, become so intense they would drown entire regions of the sky, outshining nearby planets and the Milky Way. Gamma-ray bursts, when they fire, would cut across the heavens as razor-thin beams of neutrino brilliance, brief but almost unbearable in this ghostly vision. Closer to home, the structure of the galaxy changes completely. Invisible light, dust hides the galactic center behind a thick, opaque band. In neutrinos, that boundary simply dissolves. The crowded stellar clusters packed around the central black hole shine through their dense populations of massive stars and violent interactions, turning the core of the Milky Way into a glaring knot of ghost particle light that never switches off. Then there are the storms. A nearby supernova would not just be a brightening star. It would be a sudden neutrino hurricane, a burst so intense that detectors on Earth would register tens of thousands of events in seconds. Neutron star mergers, which now appear as brief flashes in gravitational waves, would flare as sharp, spiky neutrino beacons, marking the exact moment when matter is crushed beyond nuclear densities. Compared to this, human eyesight is almost useless. Designed for a narrow band of photons, it misses most of the universe's energy budget. No one expects how much power is flowing through the cosmos in particles that pass straight through planets, spacecraft, and entire solar systems without leaving a trace. In that context, catching a single ultra-high energy neutrino is like seeing one bright flash from an otherwise invisible lighthouse, one point on the sky, one impossible particle telling scientists that somewhere out there an engine is running far beyond anything the large Hadron Collider can reach. By the end of tonight, you're going to understand why that one flash matters and why the next step is to trace it back to its source. Because the moment someone does, the quiet sky above will never look the same again. That flash in the ice feels dramatic because it is, but it only makes sense against the backdrop of something even stranger. You are already living inside a permanent storm of ghost particles and cosmic bullets. Tonight, we're going to zoom out from that single ultra-high-energy neutrino and look at the invisible weather of space that never turns off. Every second, the Sun, the Milky Way, and distant galaxies are firing particles at Earth. Not just a few, trillions upon trillions. Start with neutrinos. Every second, about 65 billion solar neutrinos pass through a square centimetre of your skin. That's roughly the area of a fingernail. They come from nuclear reactions in the solar core, fly out at nearly the speed of light, and then just keep going. Through planets, spacecraft, even through the entire solar system, as if none of it is really there. Layered on top of that is a constant drizzle of cosmic rays. Protons and heavier nuclei accelerated by supernova remnants, active galactic nuclei, and sources scientists are still trying to understand. At Earth's boundary with space, the flux is high, but by the time these particles hit the upper atmosphere, most of their energy is spent creating cascades of secondary particles long before they reach you. Here's the contrast. The ultra-high energy particles that make headlines, the ones with energies tens of thousands of times higher than CERN's collisions, are spectacular, but vanishingly rare. For every one of those that slams into the atmosphere, untold billions of lower energy cosmic rays and solar particles have already passed by, unnoticed. No one expects that to sound safe. Energy that extreme sounds like something that should scorch the ground, but Earth is not naked in this storm. It carries a magnetic field and a thick atmosphere, and together they act like a multi-layer shield. The magnetic field reaches far beyond the planets, carving out a cavity in the galactic wind called the magnetosphere. Charged particles spiral along these field lines, get trapped in radiation belts, or are diverted toward the poles, where their final energy is quietly dumped into glowing auroras. The atmosphere then finishes the job, absorbing most of the remaining radiation high above the surface. Before we get started on the next mystery, there's one reassurance that has to be explicit. A single ultra-high energy neutrino, even one 30,000 times stronger than CERN's collisions, poses no threat to Earth. It interacts so weakly that the overwhelming probability is nothing happens. No crater, no blast, no biological damage, just a faint flash in a detector if scientists are lucky. That's the paradox. The sky above is full of violent processes, accelerating particles to unimaginable energies, yet on the ground, life proceeds as if the universe were calm. By the end of tonight, you're going to understand that detectors like IceCube are not alarms. They are translators, turning that invisible rain into a readable signal. And once the signal is clear, the next question becomes unavoidable. Who, or what, is firing the highest energy shots? That question is where neutrinos stop being just ghost stories and start becoming cartographers. Each time one of these particles leaves a trace in the Antarctic ice, scientists are not just logging an event, they are putting a pin on a new kind of sky map, a map that shows where the universe is pushing matter and magnetic fields to their absolute limits. Now let's begin with what that really means. Traditional astronomy paints the heavens with light, radio, optical, X-rays, gamma rays. Neutrino astronomy paints it with impact points and reconstructed tracks, each one pointing back, within some uncertainty, to a region in space where extreme particle acceleration is happening. One lone line might not tell you much. 10,000 lines over years of solar cycles and cosmic variations start to sketch patterns. Those patterns are the real prize, clusters of events in one patch of sky, correlations between neutrino directions and known classes of objects, active galactic nuclei, starburst galaxies, maybe even the sites of gamma-ray bursts. The expectation is simple. If some population of engines dominates the high-energy universe, their signature will emerge statistically. More hits from blazars than from quiet galaxies, more events from dense galaxy clusters than from the voids in between. No one expects a single ghost particle to reveal the culprit, but together they behave like a crowd pointing at the loudest source. Energy adds a second dimension to this map. The distribution of detected neutrino energies is not random noise, it is a fingerprint of the acceleration mechanisms at work. Different models of cosmic ray factories predict different spectra. Some fall off steeply, some extend as hard power laws, some cut off sharply at a maximum energy set by magnetic field strength and size. By the end of tonight, you're going to understand that plotting energy against direction is how scientists test which cosmic accelerators are real and which are just elegant equations. On that plot, the 2022 Ultra-High Energy event sits out on the frontier. A point far from the crowded cluster of lower energy detections, probing a regime where protons and nuclei are slammed to energies 30,000 times higher than CERN can reach. It is a boundary marker, telling us that somewhere out there, beyond the familiar planets and the calm of the solar system, nature has built a machine that treats our largest collider like a warm-up, and yet we are still in the infancy of this mission. The neutrino sky today looks like radio maps from the 1940s, a few bright sources, a hazy background, and enormous uncertainty. Back then, no one predicts that obscure radio blobs would turn out to be entire galaxies with jets spanning hundreds of thousands of light years. Today, absolutely no one anticipates that the first sparse neutrino map shows the full diversity of what is out there. The data set is too small, the exposure time too short, the detectors just at the threshold of the necessary scale. Tonight, we're going to watch that change. As more years accumulate, as new detectors join IceCube in the deep sea and in mountain valleys, the random scatter will sharpen into structure. The ghost particles will outline a new cosmic geography, a high-energy overlay on the familiar constellations. And once that map is clear enough to read, the next challenge will be even harder, explaining why the universe chose those locations as its most violent particle engines. Those locations are not just pins on a map, they are power plants. And for more than a century, astronomy has been looking at them through the wrong keyhole. Traditional astronomy is built on light. Telescopes gather photons from the soft glow of visible stars to the long, cold waves of radio and the fierce flashes of X-rays and gamma rays. That picture is beautiful, but it is biased. It highlights the slow, steady, long-lived processes, nuclear fusion humming in stellar cores, galaxies shining for billions of years, nebulae glowing gently in the dark. By the end of tonight, you're going to understand that this is only one layer of the cosmos. There is a second universe superimposed on the first, one that does not care about gentle starlight. Neutrinos, cosmic rays, and gravitational waves point to a regime where everything is short-lived, violent, and extreme. In that regime, shock fronts race through space at nearly light speed, magnetic fields snap and reconnect, and particles are hurled to energies that make the largest human-built collider look like a toy. The contrast is stark. Expectation, a quiet solar system orbiting calmly inside a galaxy of orderly spiral arms. Reality, a dynamic ecosystem of cosmic accelerators and particle storms where black holes, neutron stars, and colliding galaxies pump energy into invisible beams and winds. Light shows us the glowing aftermath. Neutrinos and cosmic rays show us the engines while they are firing. Tonight, we're going to treat the 2022 neutrino as more than a curiosity. This single ghost particle, with an energy roughly 30,000 times higher than collisions at CERN's Large Hadron Collider, is a direct sample from that hidden ecosystem. It did not bounce off mirrors or scatter in clouds the way light does. It flew almost perfectly straight, across millions or even billions of light years, out of a particle accelerator built by gravity and magnetic fields rather than engineers and superconducting magnets. Before we get started on where it came from, notice what that means. This neutrino is a messenger from a regime of physics and astrophysics that is only now entering the data phase. For decades, scientists had theories about jets from active galactic nuclei and the shock waves of gamma-ray bursts. Now, a single interaction in Antarctic ice ties those theories to a specific direction in space, to a real engine running in real time. No one expects a quiet point of starlight to hide that level of violence. No one predicts that behind an ordinary-looking galaxy there might be a blazar core flinging ghost particles across the universe straight through planets, spacecraft, and viewers on a random night. Yet that is the new mental model taking shape. Every star field overhead is not a static backdrop, but a live multi-messenger network of energy flows we are only beginning to read. Now, let's begin to ask the next question. If one neutrino can redraw the map like this, what happens when we finally trace its path back to the exact engine that fired it? To trace that path, you have to leave the abstract map and drop to the very bottom of the planet where that one ghost particle actually left its mark. The South Pole Station is not a place humans are supposed to be comfortable. For months, the sun never rises. The temperature can plunge below -70 degrees Celsius. The air is thin, the horizon is empty, and the nearest city is more than 1,000 kilometres of ice and wind away. Yet, a small crew stays through the long polar night, keeping a 1 cubic kilometre detector alive so it can listen for neutrinos that almost never speak. Their world is compressed into tunnels, labs, and a few warm rooms. Day and night blur into a single dark gradient. You wake up, check the weather, check the power, check the data stream. Coffee, then dashboards, graphs of trigger rates, alerts from thousands of optical modules buried deep in the Antarctic ice. While most of the planet sleeps under familiar skies, a handful of scientists and engineers step outside into a sky that never brightens, just to walk to the IceCube counting house and make sure the mission is still running. No one expects drama from that routine. Most days the plots are boring on purpose. Flat lines mean the detector is healthy. A small spike might just be a snowstorm changing radio noise. A weird pattern might be a frozen cable or a glitching sensor. So they suit up, pull on masks and goggles and cross the ice to troubleshoot hardware in air that can freeze exposed skin in seconds. The spacecraft exploring the outer solar system have more neighbours than these people do. Then, every so often, the routine fractures. A reconstruction job flags an event that looks wrong in exactly the right way. An automated system fires off an alert to the collaboration. Phones buzz in the middle of the Antarctic night and in the middle of the day in Europe, the Americas, Asia. Someone in the control room at the pole sees the event ID first. Someone in Madison or Berlin or Tokyo opens the same plots minutes later. Before we get started on the physics, notice what happens socially. The quiet channel explodes into messages, screenshots, fast calculations. Tonight, we're going to follow that human chain as much as the neutrino's path. A late-night video call spins up, faces lit by monitor glow rather than sunlight. Senior scientists, grad students, engineers who installed the sensors years ago, all staring at the same reconstructed track slicing through the ice with an energy far beyond CERN's collisions. By the end of tonight, you're going to understand that IceCube is not just a box of instruments at the end of the world, it is hundreds of people distributed across the planet, running simulations, cross-checking calibrations, arguing over error bars, and slowly converging on the conclusion that this one event is extraordinary. Pattern interrupt. Zoom out. That one event depends on cargo flights that only come a few times a year, on fuel carefully rationed through winter, on cooks, mechanics, and medics who keep a tiny community functioning while the sun is gone for 6 straight months. It depends on people choosing to spend holidays in perpetual darkness, so that when a neutrino finally slams into Antarctic ice with 30,000 times the energy of a CERN proton beam, the detector is powered, synchronized, and recording. No one predicts their own life becoming a support system for ghost particles, yet that is what this collaboration is, a global, human scaffold built so the universe can speak in neutrinos, and so we can listen from the literal end of the world. Now, let's begin to ask what kind of cosmic engine demands that level of human commitment just to hear a single whisper. The universe has fired a bullet at the solar system. We've measured its energy, traced its path through space, and watched it carve a line through a cubic kilometre of Antarctic ice. But the one thing scientists still don't have is the cosmic finger on the trigger. Now, let's begin to untangle why that is so hard. The reconstructed direction of this ultra-high-energy neutrino does not point to a single lonely lighthouse in the dark. It points to a busy neighbourhood on the sky. In that patch there are active galactic nuclei, radio-loud galaxies, background galaxies layered behind them, and a fog of unresolved sources that current telescopes cannot separate. The neutrino's path says somewhere in here. It does not yet say this one. Part of the problem is angular resolution. IceCube is enormous, but even a cubic kilometre of ice is a blunt instrument in cosmic terms. The track of Cherenkov light lets scientists reconstruct the incoming direction to within a fraction of a degree, but not to pinpoint accuracy. That might sound sharp, but at cosmological distances, a fraction of a degree spans millions of light years and can cover dozens of promising objects. Designed to detect ghost particles at all, the detector was never meant to function like a sniper scope. Then, there is the density of candidates. In this region, several AGN beamjets of plasma into space. Some aim near our line of sight and others flare in gamma rays and X-rays at unpredictable times. No one expects a single neutrino to come with a return address label. No one predicts that one detection alone can discriminate between a blazar jet, a tidal disruption event shredding a star, or a hidden, dust-choked accelerator we have not yet catalogued. So what would it take to move from somewhere in here to this object right there? Repetition. If future neutrinos of similar energy arrive from the same region, especially clustered in time, the statistics start to shift. A burst of neutrinos within days or weeks, overlapping with a flare from one particular AGN, would be a powerful multi-messenger signature. By the end of tonight, you're going to understand why scientists are now watching that patch of sky like a crime scene, waiting for the universe to fire again. To help them, new gamma-ray and X-ray surveys are sweeping the sky more deeply and more often. Time-domain astronomy is transforming static star charts into live video, catching brief, violent outbursts that older missions missed. A previously unknown flaring source in the neutrino's direction could suddenly light up, turning a vague trajectory into a direct accusation. For now, though, this remains an open mystery. The mission has the bullet and its rough trajectory. The smoking gun, somewhere far beyond the edge of our solar system, is still hidden in the glare of the distant universe. And absolutely no one anticipates what will be revealed when the next ghost particles arrive from the same celestial address. So if one ghost particle left a clear bullet hole in a cubic kilometre of ice, how many others slipped through the solar system without a trace? How many shots were fired that no detector on Earth ever even noticed? To answer that, you have to think the way the mission designers and scientists who built IceCube think. This observatory is enormous by human standards, but from the neutrino's point of view, it is a tiny keyhole in an ocean of space. The instrument watches about 1 cubic kilometre of Antarctic ice. Earth's volume is more than 1 billion times larger. The sky above it is effectively infinite. IceCube's effective area and duty cycle mean it only samples a fraction of the neutrinos that actually pass through Earth and its surroundings. It looks down through the planet, using Earth itself as a filter, and waits for the rare interaction that lights up the array. Trillions of lower-energy neutrinos stream through every second. Almost all ignore the detector completely. The ultra-high-energy ones are rarer, but the same rule applies. Most never hit the sweet spot of ice at the right angle with the right interaction at the right time. Now, let's begin to narrow that down. Even when a ghost particle does interact, the detector is not omniscient. Thresholds, geometry, and analysis cuts are brutal gatekeepers. Sensors must see enough Cherenkov light. The reconstructed track must be clean, not confused with atmospheric moons or background noise. Events near the edges can be mis-reconstructed. Some are discarded by automated filters. No one expects every cosmic bullet to leave a perfect, cinematic trail. For ultra-high energy events, the odds are still against a clean catch. Depending on the exact energy and direction, models suggest that for each detected neutrino of this scale, many more pass through Earth unseen. Some estimates imply tens, maybe hundreds of comparable or even more energetic neutrinos could have crossed the planet during the same observing period. They sliced through rock, ocean, spacecraft, and planets in the solar system, depositing nothing that any instrument could record. Tonight, we're going to think of that single detection not as an isolated miracle, but as a statistical hint. By the end of tonight, you're going to understand that each bright track in IceCube is the visible crest of a much larger, invisible wave. Our current view is a tiny aperture into a much busier, high-energy universe. A universe where extreme accelerators beyond the heliospheric boundary fling out particle storms that almost never announce themselves. No one predicts that 1 cubic kilometre of ice can reveal the full violence of that universe. If this is what we can see with this lone frozen eye at the South Pole, what storms are raging out there that every detector on Earth is still blind to, and what happens when the next ghost does not miss quite so cleanly? So the next question almost asks itself, if 1 cubic kilometre of ice can catch a single ghost, what happens when scientists build 10 or 100? Tonight, we're going to step into the design room and watch the next generation of ghost catchers take shape in the most remote corners of our planet and far beyond it in space. The first upgrade has a familiar name with a very unfamiliar scale, IceCube Gen 2. Think of the current detector as a prototype that accidentally changed the game. Now imagine stretching that frozen observatory into several cubic kilometres of Antarctic ice, with more strings of sensors spaced wider, tuned to the brightest, rarest tracks. The mission is simple to state and hard to overstate. Catch the highest energy neutrinos with enough frequency that they stop being legends and start being a data set. In practice, that means denser instrumentation where low-energy events whisper, and sprawling, sparse arrays where ultra-high-energy neutrinos shout. More digital optical modules, more precise timing, better calibration of the ice itself as an optical medium. The boundary between we saw something and we reconstructed a full 3D trajectory with a birth certificate and a return address begins to blur. By the end of tonight, you're going to understand why adding volume in the right way multiplies sensitivity at the very top of the energy ladder. But optical light in ice is only one channel. Pattern interrupt. What if the best way to catch a neutrino is not with light at all, but with radio waves? When a truly extreme neutrino slams into Antarctic ice, it can create a particle cascade that emits a sharp, nanosecond-scale radio flash. Radio waves travel far, and antennas are cheap. So scientists are planning vast radio detection arrays spread across the surface and embedded just below it, listening for those brief, broadband chirps from below the snow. Projects like RNOG in Greenland and proposed arrays at the South Pole aim to monitor volumes far larger than any optical detector could afford to instrument. Add balloon-borne experiments drifting above the polar plateau, scanning thousands of square kilometers of ice for radio bursts from below. No one expects a single antenna to catch much, but an army of them, synchronized and staring at the same frozen target, turns the entire polar cap into an enormous, cost-effective neutrino telescope. And then the concept jumps completely off the Earth. Space-based observatories in low orbit or even higher would watch the night side of the planet for faint, optical or ultraviolet flashes in the atmosphere, triggered when an ultra-high-energy neutrino creates an air shower. From that vantage point, one spacecraft can monitor millions of square kilometers at once. The whole planet becomes the detector. The atmosphere becomes the screen. No one predicts every concept will work on the first try. But absolutely no one anticipates going back to the era where ultra-high-energy neutrinos are once-in-a-decade curiosities. With IceCube Gen 2 radio arrays on the ice, balloons overhead, and spacecraft watching the limb of the Earth, those ghosts turn from isolated case files into a population that can be mapped, catalogued, and compared across the sky. Now, let's begin to ask a deeper question. Once the map appears, what engines out there in the cosmic dark are powerful enough to light it up? Those engines in the cosmic dark are not abstract diagrams in a paper. They are aimed, right now, at you. Step outside in your imagination for a moment. Clear night, no clouds, just you. The planets wheeling silently overhead, and a sky that looks calm but is anything but calm. Through your skull, through your chest, through the entire solar system, ghost particles are pouring. Trillions of neutrinos from the sun and distant galaxies stream through your body every second. Most glide straight through Earth as if the planet were transparent glass. A few very rarely hit something. One of them in 2022 carried 30,000 times the energy of a collision at CERN's large Hadron Collider. It crossed interstellar space, threaded the galactic wind, and chose the tiny boundary of a single atomic nucleus under the South Pole as its stage. Tonight, we're going to connect that invisible collision to the way you stand under the stars. Because understanding these particles is not just an academic exercise in exotic physics, it is part of understanding how energy actually moves through the universe, how violent engines in distant galaxies sculpt the large-scale structure that every spacecraft, every mission, and every living thing is embedded in. Think about how this relationship has changed. Not long ago, a bright comet meant omens and disaster. A solar eclipse could send entire cities into panic. The sky was a theatre of unpredictable signs, not a system that could be measured. Now, scientists bury glass spheres in Antarctic ice and wait for a single blue flash that says, a neutrino from beyond the Milky Way just passed through the planet beneath your feet. The contrast is staggering. Once, humanity feared shadows on the moon. Now, detectors can register a single ghost particle that has crossed millions of light years without stopping. Once the boundary between Earth and space was a hard line of myth. Now, that boundary is a data stream, where solar wind, gamma rays, and ultra-high-energy neutrinos are all logged, time-stamped, and traced back to specific galaxies. No one expects a species that once told stories about dragons swallowing the sun to end up measuring the angle of a neutrino track to fractions of a degree. No one predicts that the same brain that once mapped constellations as gods would one day map the arrival directions of particles with energies 1,000 trillion electron volts. And absolutely no one anticipates that, by the end of tonight, you're going to understand that you are living at the moment this transformation becomes routine, because that is what is really happening. The shift from superstition to precision measurement of ghost particles is not just a scientific upgrade, it is a change in how a conscious species relates to the cosmos. You are part of a civilization that can now listen in a very literal sense to the whispers of a violent universe. Each detected neutrino is a syllable in that whisper. A message from a jet near a black hole or a shock front where galaxies collide. So the next time you look up and feel small, remember this: you are not just under the sky. You are inside a vast, dynamic system permeated by signals that your species has learned to decode. The question now is not whether those signals exist. The question is, what happens when we can read them fluently and follow them back to the engines that launched them? That is what this single event really is. A signal, a whisper in the ice that, when decoded, turns into a story stretching from the edge of a galaxy to a flash of blue beneath the South Pole. Now, let's begin to trace that story cleanly from end to beginning and then forward again. Start with the last frame. A charged particle racing through Antarctic ice faster than light can move in that medium, leaving behind Cherenkov radiation, a cone of blue that IceCube's 5,000 optical sensors record as a sudden geometric bloom. To the detector, it is just a pattern of photons. To scientists, it is a map. Run that map backward in time. From the angles and timing, the team reconstructs a track pointing in from deep space, not from the atmosphere, not from the sun, but from far beyond our solar system. The culprit is not the streaking particle itself, but the ghost that created it. An ultra-high-energy neutrino that slammed into a nucleus in the ice after crossing millions, maybe billions, of light years without flinching. By the end of tonight, you are going to understand why that is so shocking. Trillions of neutrinos from the sun pass through your body every second. They ignore planets, spacecraft, even entire stars. No one expects one of them to arrive with an energy 30,000 times higher than the protons in CERN's large Hadron Collider. No one predicts that a single collision in a cubic kilometre of frozen water will outclass the most powerful machine humans have ever built. Yet that is exactly what this event represents. A natural particle accelerator somewhere out there took magnetic fields, shock waves, and jets and wound them up to energies that terrestrial colliders can only dream of. The leading suspects live in the most violent neighborhoods in the universe, active galactic nuclei with supermassive black holes at their centers, blazars whose jets happen to be aimed almost directly at Earth, gamma-ray bursts that detonate like cosmic flashbulbs across entire galaxies. Each candidate tells a different version of the same story. If the neutrino came from a blazar, it means those jets are not just bright, they are efficient factories for cosmic rays. If it came from a hidden active nucleus, it means there are engines buried in dust and gas, invisible in light, but blazing in neutrinos. If it came from a gamma-ray burst, it ties the death of massive stars to the highest energy particles known. This is where disciplines collide. Particle physics uses the neutrino as a probe of fundamental interactions at energies no accelerator can reach. Astrophysics uses it as a tracer of extreme magnetic fields and shock fronts. Cosmology uses it to test how space itself behaves when particles cross a significant fraction of the observable universe. Tonight, we're going to treat that tiny flash as a boundary marker. On one side, a world where the most extreme processes were theory, modelled on screens and chalkboards. On the other, A world where a single, well-interpreted signal forces those models to confront reality. Because if one ghost particle can carry this much information, the real question becomes, how many more are already on their way, and what new engines will they reveal when the next flash appears in the ice? That question hides a deeper paradox. A single ghost particle carries more energy than the most powerful machines ever built, and yet life goes on. Oceans stay calm, cities don't blink. Most people never even know the shot was fired. Every second, Earth is under fire from the rest of space. Ultra-high-energy neutrinos, cosmic rays, gamma rays from distant explosions, the constant wind of particles from the sun. Cataclysms on other planets and in other galaxies are literally aimed at this tiny world, and almost all of it is stopped by a few fragile-seeming layers. A magnetic field, an atmosphere, a thin shell of rock and water. Expectation versus reality. The expectation is that a violent universe should be uninhabitable, that a solar system bathed in radiation and shock waves must be a dead zone. The reality is that those same processes helped build the boundary conditions that protect this planet. The solar wind inflates a bubble that shields the inner planets from much of the galaxy's rawest radiation. Earth's molten core powers a magnetic field that deflects charged particles. The atmosphere turns lethal energy into auroras and scattered light. So, understanding these violent engines does not suddenly make the cosmos more dangerous. It does the opposite. It shows that for billions of years this mission has been running. A natural spacecraft called Earth, wrapped in self-generated shields, threading its way through a shooting gallery and still making oceans, weather, and biology possible. Before we get started on fear, it is worth noticing what has already been survived. Gamma-ray bursts have flashed somewhere beyond the spiral arms. Supernovae have detonated and hurled out shock fronts. Black holes have flared as they fed. And yet, under a few kilometres of air, a few microteslas of magnetic field, complex cells arose, then brains, then scientists able to build detectors in Antarctic ice and ask where these ghost particles come from. By the end of tonight, you're going to understand that learning a neutrino can outgun CERN by a factor of 30,000 is not a threat. It is a calibration. It tells you the true scale of the accelerators out there and the true sophistication of the shields right here. It turns the sky from a blank dome into a dynamic system of engines, beams, and barriers. Emotionally, that changes the relationship with the cosmos. The unknown is frightening. A mapped battlefield is awe-inspiring. Now, when a neutrino crosses the detector, it is not just a random glitch. It is a message from a blazar or an active galactic nucleus beyond the visible edge of comfort, proving that this tiny world is connected to events far outside the local solar neighborhood. Tonight, we're going to lean into that connection. Because if one ghost particle can redraw the sense of safety and place, the next step is obvious. Follow more of them. Trace more paths. Turn fear into a roadmap. And the real surprise comes when those maps start pointing back, not just to where we are in the galaxy, but to how we got here in the first place, and what might be waiting just beyond the next invisible shot. So now that one ghost particle has carried you from a distant accelerator to a cubic kilometre of Antarctic ice, there's a quiet question hanging in the air. If you can follow that, what else can you follow? You just tracked a single neutrino across billions of years and light years. That is not a casual use of attention. Without being told, you practiced a new way of seeing space. You pictured the solar system not as a flat diagram of planets, but as a target in a cosmic shooting gallery, with ultra-high energy particles threading through magnetic fields and solar wind. You held in your head that this one neutrino carried about 30,000 times the energy of a proton collision at CERN, and yet it left almost nothing behind. That's a skill. Comparing scales that no one expects the human brain to juggle comfortably. By the end of tonight, you're going to understand that what just happened here is training. You learned to visualize a neutrino interaction as a flash of Cherenkov light in ice. You watched scientists reconstruct a path from a handful of photons and a small timing difference between sensors. You started to think like a multi-messenger astronomer, where one event is never just one thing, but a clue that has to line up with gamma rays, X-rays, and gravitational waves. So tonight, somewhere a kilometre beneath the Antarctic ice, those 5,000 glass spheres are still watching. They are still waiting in perfect darkness for the next flash of Cherenkov blue, the next signature of a neutrino that crossed billions of light years and somehow, on its way through everything, decided to interact with one nucleus in the ice. The detector is silent the way a microphone is silent before the sound arrives. The universe has not stopped firing. Somewhere, in a jet wrapped around a supermassive black hole or in an explosion that bends the rules of energy, another ghost particle is already on its way. It has already forgotten where it came from, but the ice will know. There is something steadying in that. The detector does not need to be watched to keep working. The neutrinos do not stop arriving when the recording instruments are off. Trillions are passing through you right now, through every continent, every ocean, every star in the visible sky, and almost none of them will ever interact with anything at all. The few that do will leave their tiny scar in the ice, and the patient instruments will read it. And somewhere, eventually, a scientist will look at a plot and understand a piece of the universe that no one understood before. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.